Okay, now I share my screen.
We can see that perfect.
Okay, great.
So we'll give a minute more to some people to drop in, and there's
Of course.
a group of people that are already in the room and getting snacks and drinks. So I will be happy to introduce you, and then unfortunately I have a committee meeting at 2:30 p.m. that I need to step out.
No problem.
One of our great students, Santiago, handle
Sure.
the questions and answers, but we really look forward to your talk. So do you want to try to do full screen, or is it already full screen? And
No, I will do full screen.
Okay.
Now.
Great.
Does it work now?
Yeah, that's perfect, because sometimes
Okay.
things don't work the way you're supposed to work. Okay, great. Okay, let's give a few more seconds and a reminder. Okay, so if you're ready, I'm happy to introduce you.
Yeah, I'm ready.
Okay, well, it's my pleasure to introduce you to our former and great colleague, Jishen Zhao, who is currently an associate professor in the Computer Science Engineering Department at the University of California, San Diego. She does work on boundary of computer architecture and systems, specifically on memory systems, machine learning, or computer and dynamical systems and reliability. So she was here at UCSC, and before that, she was a research scientist at HP Labs. She has several awards, including the NSF Career Award, the AWS AI Amazon Research Awards, and several Best Paper Awards, in addition to being a member of Micro Hall of Fame. So Jishen, is very great to have you here, and the floor is yours.
Thank you so much, Ricardo, for the introduction, and really happy and thank you for having me here. Give a talk. I really want to be on campus, but due to family reason, I can. Hopefully, sometime later, I will hop on campus again and see everyone in person. But today, I would like to talk about one of our research area, a few works in the area related to reliability and safety of autonomous driving computer system design. But before I get started in that topic, just let me briefly introduce our research. I guess some of you may already know my research when I was in Santa Cruz a few years ago. So I basically work on memory architecture and systems design, but I also work on, of course, other methodologies that apply to the computer architecture and memory system design, like machine learning is one of the areas we're working on currently. So we work on how to leverage the existing and also develop some of the new machine learning models to help better design the programming and also the system scheduling of memory systems. But we also work on how we can explore the memory system architecture design to better support the reliability of various applications. Like one application area that I'm going to focus on today is autonomous driving applications. So regarding autonomous driving safety or autonomous driving system design, we have a few kind of platforms currently we have been working on. One is at UCSD, we have a couple of actually self-driving vehicles running on campus. And this figure is one of them. It's a mail delivering vehicle that has some of autonomous capabilities. And we also collaborate with some of industrial autonomous driving players, like some of startup companies that testing their auto driving cars various across the country. And also we recently collaborated with NVIDIA to explore the safety-aware systems design and frameworks that help to test the safety of the autonomous driving cars before the production. So why safety and reliability is important? If you talk to a lot of the self-driving car vendors or the self-driving car developers in the past few years, maybe 4 or 5 years ago, people really care more about how to put the car on road and run and high efficiently. But lately, there have been a lot of the attention have been placed on the safety and reliability, because now when we're seriously considering to adopt a self-driving car, that imagine you're going to sit in there, you care about your life, you care about whether it's safe enough, whether it can avoid the collision or accident, whether it can drive you to everywhere without too much of the tension that watching the car how it's operating. And also there's a lot of government and research associations effort on formalizing the rules for safety of autonomous driving cars. As one of our experience in the past, when we work with a self-driving car company on a road test, when we do our field study, this is one example that we captured the near collision or safety critical scenario is when there's a yellow light, this car. So this view is from us as a self-driving car that we're prepared to kind of like, because although it's yellow light, we can still cross the road. But at this time, pay attention to this white car. It's already, because it's yellow light, so it's prepared to kind of cross the cross section, enter the cross section as well. And actually it's entered the cross section so fast that we're still on the road. We kind of already come across this white car. So the self-driving car the driver actually needs to take over and place a hard brake to kind of avoid the collision. So it shows that as a self-driving car, although normally in normal operation, you can kind of keep it safe, but there's always some safe to critical scenarios. In some cases, they need to react fast and react safely to avoid collision really happen in those safe critical scenarios. So that speaks for the importance of studying or researching the safety of self-driving cars. But when we study the safety of self-driving car system design, we also find some of the challenge specifically for systems, because speaking for self-driving car safety, safety can be studied in various levels, like from the applications algorithms level, from the area level rules, and the reliability of the hardware design particularly also. But our group thinks we focus more on the systems and architecture design. We care, or what matters more to us is what the challenge or issues we're gonna tackle at the systems and architecture level. So as we see as a self-driving car, we focus more on the computer system inside self-driving car. So it's more like a driver of the car. So there's different types of the computing systems people have been considering. So people have been working on reliability and fault tolerance of various computing systems, can also maintain some of the reliability and what we call safety as well. But we found that self-driving car is, in some sense, quite different from those systems. So, question? Feel free to interrupt me if you have any questions anytime. If not, then we're going to continue. So first of all, self-driving car systems is as computer system, it's a mission critical system. So it requires the reliability, the levels of reliability and fault tolerance guarantees are very high. So take an example, if there's a blue screen in your laptop, in your computer, or some error pops up, it's okay. It can take like a few minutes or even an hour to fix it. But if you're running on road at a very high speed, a kind of dead on the car computer is actually world worst of life of a human, right? But at the same time, the computer system on the self-driving car, the design itself for the resource allocation itself are very different from the traditional computer systems. So compare the self-driving car systems versus different types of computer systems we have worked on a lot in the past decades. Versus cloud servers, I know many of you have been working on cloud systems. Cloud systems has a lot of redundancy, and also the budget constraints are much relaxed compared to you have just this one or a couple of computing nodes on the card, and that's it. And also, I'll show you later on of our profiling results. We found that it's also different from the cloud servers, is that cloud server is sitting there, it's always there. So the kind of data and the computation dealing with is relatively static in terms of location. But a computer on a car actually is moving. So we show that it's the type of data or the patterns of the data and also the computation, the processing is highly correlated to the dynamic environment, like the moving direction, like a traffic density, so on and so forth. And it changed really fast. And second is that compared to the real-time systems, because you might imagine that the traditional computer on the car, it's not autonomous driving, it's embedded system itself or real-time systems. But autonomous driving computers, because it needs to deal with a lot of like sophisticated computation tasks. So it's a high performance computer. And I'm going to show you later on of our study, we found that it's actually almost like server grade or high-end computer nodes, computation and memory and storage nodes there. And compared to when I talked to one of the startup company which supplies the chips for the self-driving cars, they talk about the ways that self-driving cars to support reliability safety might be similar to the way where the air spacecraft systems. But a key difference we found there is the cost constraints. So we have less likely we're going to have like stringent cost constraints, the money in the space or aircraft systems. But as a car, it's a consumer market. People care about like how much money they're going to pay. So you cannot spend like millions, thousands of millions of money just to maintain the safety of a self-driving car system. So these are differences compared to traditional computer systems that we need to take into account when we design the self-driving car system towards the safety guarantee. Not to say that self-driving car are typically going to have a car as a car. You can typically, like I'm still driving my car that I bought maybe 10 years ago. So we need to kind of ensure the reliability and safety for a longer lifespan compared to a lot of the traditional computer system as well. So I'm motivated by these challenges and importance of safety-aware system design for autonomous driving. In the past few years, we have been, actually that effort started when I was still in Santa Cruz and spending all along up until now. We have been studying across the stack, various system stack of the autonomous driving computer systems. So we have been studying the application level. We develop characterization tools and also develop hardware-aware self-driving car software modules. And we develop system level resource management like Linux containers. And we also spend a lot of effort, of course, on our expertise is in computer system architecture design to really study how better to manage the resource of the various computation and memory and storage resources. And at the bottom, we also develop tools and characterization experiments to better understand the safety requirement to the system of autonomous driving. So because there's quite a lot of work, if you're interested, you can take a look at those papers on the list that list over here. But I'll perhaps just pick a few of those that I thought might be of interest to some of you. to talk about, but if you're interested, I'm happy to talk offline later on about other works. So I'm going to start from the bottom. That is the understanding of the safety requirements of autonomous driving computer systems. So in that sense, we developed a lot of the frameworks and also the characterization experiments and deliver some of the results to reflect what is the safety requirements of autonomous driving computer systems. But first of all, let's start from really the outside or the top. What is the state of art autonomous driving computer system look like, or high automation autonomous driving computer system look like? High automation means that higher level, that is, the car can drive around by itself most of the time, unless really need the human driver to kick in some critical scenarios. So what we found when we look at those industrial self-driving car computer systems, we found that the computation and also the storage and also the system software running on those hardware are very sophisticated, are very high end. So, for example, on the top level, a car has a lot of sensors and also needs to process the sensor data at real time. But what's at the heart of this car, that's the driver of the car, that's the computer system inside there, actually has high-end, like the Intel Xeon processor, for example, that the car we were using in a field study earlier, and also has discrete GPU cards like GTX 2080 or that scale, or maybe have multiple of them. And of course, it has memory, has SSD drives, just like almost like a server system. And it's running Linux operating systems like Ubuntu. And of course, on top of that has robotics control libraries like ROS or anything else. Our work also adds one layer of the Linux container on top of that to manage all those Linux and also application functions there. So there's very complex software system running on a complex hardware system, and it's a heterogeneous system. Here's just a very simple hardware configuration, but you can imagine you can add accelerators on top of FPGA and multiple of the computing node. Like some of self-driving cars may have like 2 or 4 of this kind of nodes working together as a distributed system. And speaking for what kind of software modules or tasks running on the autonomous driving system, this is a AutoWare software AV stack, one of the widely used AV platform people have been playing around with. As you can see, there's localization, there's the planning, and there's perception, that is the interpret the sensor, camera, and LiDAR data, and they need to work together and map it to the computer systems. So what kind of tasks being run on a computer system of our autonomous driving car? As you can see, we can divide the computation tasks into 3 types of tasks, like localization, that is to decide where the car is and where the car is going. And then the perception, like I said, is to interpret the traffic around the car. And then planning control prediction is to make the real reaction to on the road. And we found that most time consuming tasks, at least of the car that we have been working on, is the perception, because it needs to process the very complex LiDAR and camera radar, all the sensor data, and then sometimes need to perform a fusion of all those data and their complex machine learning models and also non-machine learning algorithms. And the system that we profiled, what we found is that a large portion of the computation time and resources are spent on LiDAR perception, or LiDAR and camera perception. But of course, you can see different workloads are also running on the autonomous driving computer systems. And this is a more detailed view of all those modules. Due to the legal, so we cannot expose the actual name of each module, software module in there. We just gave some like high-level name of those modules. But what I want to show here is that those are very complex software modules running on the just for the perception task, and then they're interdependent because sometimes one module, the start point of the one module depends on the completion of the previous module. So there's a very complex relationship between the software modules, and a lot of them. So that makes our analysis and also the design of the computer systems really challenging because of this complex software modules and also time-consuming tasks. And that will lead to also the complexity of guaranteeing the safety and reliability of the autonomous driving computer systems. But if you are wondering what is what means by safety or reliability of autonomous driving, there are actually already definitions out there formalized. So typically in a vehicle safety area, people talk about safety in two different categories. One is called functional safety, or as a computer systems engineer, or as we work on computers, we can also almost call it reliability. So what is take care of is that integrated and fault tolerance of system, of course, both the software and hardware system. And there's already quite a few rules. For example, many of you may be familiar with ISO 26262, that's for vehicle functional safety particularly. But there's also another type of category of safety that is nominal safety. So nominal safety is that assuming the system already ensure the functional safety that is fault tolerant and reliable in terms of software and hardware, but still safety is not guaranteed fully, because you need to make sure that the autonomous driving car or because autonomous driving car is also a robot system, so this as a whole need to make timely and safe logic decisions and actions to whatever is happening right now. So what we care more about, because the safe logical decisions of algorithm designs matter. So as a system design, maybe we care even more about the timely, so the latency or the performance of the computing system, whether it can make the timely decision to certain or timely reaction to certain events happening there. So that's what our study, most of the study focus on, to want to make sure our computer system design can make the timely decisions and actions of the autonomous driving car. So there's some safety models for autonomous driving already in the nominal safety area, or this to make the timely decision. But most of them the models are based on the notion of safe distance. So that is, if there are two cars, the car needs to make sure the response is timely, so that the car, if the other car or any traffic around happens, and events happen, it can still keep the safe distance. But if we think about it, actually it's it takes the car, this autonomous driving AV, altogether as an agent, but it does not provide specific safety requirement to the computer inside it. So it cares, it actually focus on the whole car, but as a computer engineer, we want to focus on the computer design specifically. So what we will be focused on is how we can map those safe distance, this kind of requirement to the computer system design, or specifically the latency or the response time of the computer system, or the latency requirement of the computer system. So this is our main focus or main goal of our computer system design. So how to design a computer system that can meet the reaction time requirement to ensure the safe distance of the autonomous driving with any of the objects on road or traffic on road. So a little bit more detail about reaction time, that is, or the type of latency for our computer system design. As you can see, reaction time can change and is very critical to safety. So taking a previous example that I've shown at the beginning of my talk, that this white car quickly move and across the intersection of the road and appear quickly in front of a car. What happens as the car in the perception module is that in this second, it only enters from here. So it's still maybe at the edge or even out of the region of interest. So in this frame, at least the processing is not really kind of focused on it or started yet. But quickly, just in a very small or short time interval, it enters and appears in front of the car. So from time 1 and time 2, the reaction time allowed by the self-driving car may be really, really short. But it's not a kind of normal case or general case, because most of the time it does not have this quick reaction time requirement. So our goal is to ensure that in the general case, the car is running efficiently, but once there's some safe critical scenario, it requires really quick reaction time. The car can still meet that reaction time requirement. So one of our work is to better understand the computer system design requirement to guarantee safety of autonomous driving. We've done that study based on our field study of in 2019 summer, collect the data by running the level 4 AV fleets in various locations, road conditions, and traffic patterns on road. And we took that data and analyzed the data and tried to come up with a model can better understand the safety or reaction time requirement of the autonomous driving computer system design. So what we found is that there's actually a way to map the safe distance to the reaction time requirement for the autonomous driving computer system design by some complex equation over here. If you're interested, you can take a look at paper. There's a whole many pages to derive this equation. But what I want to show here first is that this reaction time and also the safety requirement reflected at reaction time requirement is related to a lot to the external factors. For example, the road condition, the weather, and also the traffic density. That is, how many cars are there, whether the traffic's busy, and whether the front car will make some kind of action that is not expected, so on and so forth. And the other thing is the nonlinear relationship between the reaction time requirement and the safety. So as you can see here, if we correlate the safe distance or the distance between two cars, the opposite driving car and the car in front of it, and the response time that the car can process, for example, the LiDAR information or camera information, that has a nonlinear correlation. That is easy to interpret in the way that if the distance between the two cars are closer, it takes maybe longer time to process, but the requirements of the reaction time are actually shorter. Okay? It takes longer time because this car appears bigger in front of the self-driving car. So it may occupy multiple grids of the perception the processing unit, so that it will take more time to process all those grids that containing this front car. But at the same time, the reaction time window is shorter, so it needs even faster reaction, so that the safety requirement is a bit more stringent in that case. But that relationship is nonlinear. So there needs to be a way to come up with the methodology to model this nonlinearity. And this is one of our methods. Again, I'm not going to get into the detail of the equation due to the time, but if interested, you can take a look at our paper. But basically what it does is that it can give you some analysis or give you some of the guidance on how much of the reaction time requirement will be needed to guarantee the safety of the autonomous driving computer system, and given a different distance and also the speed of the car and also acceleration of the self-driving car, and can find on this map. And also, as you can see, it's nonlinear. So in certain region along this curve, safety and reaction time, the relationship is not that critical. That is, you can kind of make the computer system design to, or you can schedule the computer system processing resource in a way that we can relax a little bit without impacting the safety too much. But if you enter certain region, that the reaction time requirement is more stringent, that means you need to allocate more computation resource to produce really fast reaction time to ensure the safety. So by providing the kind of model can give the autonomous driving computer system engineers some kind of guidance on how we're going to allocate a computation memory resource given certain traffic and also the computation configuration and also software design on certain autonomous driving scenarios. That nonlinear reaction time or latency of the computer system can also help us a better way to provide a prediction of the reaction time of a computer system on the autonomous driving systems. So for example, because we identified that the reaction time of our driving computer system, especially in the perception module, has a very close correlation with the traffic density, that is traffic around it, whether how busy the traffic is, how many of the objects or what we call obstacles around the self-driving car. We can give a kind of accurate enough, good enough estimation of the reaction time prediction ahead of time. And then based on that prediction, we can help the system to schedule the computational resource ahead of time to still meet the safety requirement. So this prediction module is like, given the obstacle density, there's a traffic density in there, and then we can map this density on our grid model and then come up with a prediction of, and also feeding different computation resource available on the computing system, like how many GPUs are there, how many GPU cores or CPU cores available there, and then come up with a prediction, good enough prediction of the latency. So put everything together with our safety analysis and also our prediction of latency, we show that we can give a very good kind of prediction of the level of safety of a self-driving car given a computer system design. So our goal is in this work, particularly, is to provide this framework or tool and also model to help with the computer system designers to tell when and how to design a computer system to achieve a certain reaction time in a particular driving a car or traffic scenario to maintain the certain safety level of the autonomous driving car. So this is one that I want to talk about at this level. The other recent work at this level of safety model and evaluation framework for autonomous driving computer system design is that we also developed framework to analyze the safety implications of autonomous driving systems. For in particularly, our framework can help the designers to decide if we degrade certain component level parameters. For example, we degrade the GPU clock frequency, or we degrade the camera FPS to a certain level, can we still ensure the safety? Or how much of those the component level parameters, at what level we can guarantee safety. So in particular, we collaborate with NVIDIA to look at their simulation and also the autonomous driving platforms. And what we found is that this kind of framework is very helpful for production AV designs, because before we produce a computer system for autonomous driving car, we should know how much safety level we can guarantee and how much of the flexibility level that we have on both the hardware and software design. But the challenge is particularly in designing such a framework is that actually there's threefold. First is that the autonomous driving systems are composed of many different software and hardware components. Like in the software sense, there are machine learning models, and then each model can have a trade-off between the accuracy and also its model size and the way you run a model. And then there are sensors, different sensors. And for example, cameras, you can set a different FPS, frames per second, those parameters that you can set. And also there are computation resources like GPUs and CPUs and also other accelerators. So it's hard to orchestrating all those hardware and software components and assign proper requirements to all of them at the same time to ensure the efficient and also the optimal assignment to ensure overall AV safety. So it's kind of a lot of components there, how we can make sure our requirements, like performance or accuracy, all the requirements assigned to them can ensure the overall AV safety. And the other is that currently, the metrics that we derive or out there, it's still hard to offer sufficient insights into the safety impact of different component level design choices. And the last challenge we found is that the search space, because there's so many low-level components, and the safety, as we studied earlier, previous I've mentioned, is a very complex metric to evaluate. So the search space or the design space is very big. So it's kind of hard to go through or exhaustively search of this design space. So our goal now is to how we can automate this analysis or the search of the to kind of coordinate among all those parameters in the low-level components across the software and hardware and autonomous driving computer systems. So our framework, our solution is a framework to automate the process. So input to our framework is a few of external and internal configurations. And the output of the framework, of course, is the safety evaluation result. We also take the autonomous driving simulator. We actually can adapt to various different autonomous driving simulators as the front end to simulate the autonomous driving car, the safety on the road. So looking into more details, the input to our framework, first is the driving scenario categories. So there are different types of driving scenarios. That means there are different cases when the autonomous driving car is on road. It can be placed in different cases. Like it can follow a vehicle, like there are car in front of it, or some car in front of it can make some action, like cut in or cut out, and so on and so forth. And it can also meet some pedestrians, that people walking in front of car. So those are all driving scenarios, and we give a driving scenario categories that can help us better analyze the safety of the self-driving car in these scenarios. The other input to our framework is the parameters. So that is related to those low-level components that the parameters can be configured for those low-level components. For example, the sensor capability, like I mentioned earlier, FPS of the camera, GPU frequency, and the number of GPU cores that can utilize, and so on and so forth. And one of the other input is also the time budget. That is a reaction time requirement that can be mapped to the safety requirement of the self-driving car. And our framework consists of the safety evaluation and also the safety sensitivity analysis. And of course, we can leverage the existing like the safe distance or reaction time requirement as the safety quantification metrics that can also be included into our evaluation framework. By interacting with the AB's autonomous driving simulator, that we can give a certain estimation of the level of the safety based on our safety metrics, given those inputs to our framework. So I'm not going to get into the detailed implementation of our framework, but rather I want to show you some of our characterization or analysis results that might be interesting, sound interesting to some of you. So our analysis, we took the driving scenarios based on certain driving condition, and our driving condition we assume here in this particular study is the urban expressway. And we categorize all the driving scenarios, or the safety critical driving scenarios that we care more about, into 4 types. So as I listed listed examples over here, first is the vehicle following. And a case when a vehicle following becomes safety critical is when, for example, this is our autonomous driving, this is the front car. The case when the front car not the front car brake is broken, it should be a brake, sorry for the misspelling, stop suddenly. So in that case, the self-driving car needs to make some action and need to react quickly to avoid collision, because the distance is shortening. And the other scenario is cut in, that is the car in another lane or the neighboring lane at the beginning with a slower speed suddenly change the lane. And so this is another safety critical scenario that the car again needs to react quickly to this sudden event. And the third is cut out, that the car in front of the self-driving car changed the lane suddenly, but just change the lane will not lead to any safe critical scenario unless there's some object or obstacle in front of it, maybe some other car, or maybe some static obstacles. So that will be a safety critical scenario as well. And the last category that we analyze is the jaywalking. That is a person walking in front of the another car or a static obstacle, and suddenly it appears in front of our autonomous driving car. So we also need to react quickly to avoid to have a collision with that walking people. So all of those are safety critical scenarios, all those 4 categories that events happen suddenly, and that the autonomous driving car needs to apply hard brake or a sudden reaction in a really short amount of time to avoid a collision. So there are parameters that we can tune at the low level, component level, and also our corruption models that we also tune in our experiment analysis includes in this table. We tune all of the software and hardware parameters, maybe by fixing some of the parameter and tuning the others. So in terms of software parameter, we tune the machine learning model precision and also different types of machine learning models with the strength of the capability of the model. In terms of the hardware parameters, what we tune is, in our study, we tune the camera frames per second parameter, and we'll also tune the GPU frequency. And those are the levels that we study in our analysis. In terms of the corruption model, we introduce some of the random noise and also obstacle distance and velocity change in our world model to explore the limitation of the driving safety tolerance. And these are all of the parameters we tune in terms of the noise that we introduce. And we also introduced some of inaccuracy of the world model prediction in the form of obstacle perception delay that we adding, and also the world model loss in the frames. So these are all the parameters we tune in our analysis. And the experiment hardware and software configuration is as follows. We analyze our framework on both the NVIDIA DriveSame on the level 2 autonomous driving car, and also we demonstrate our framework with other AV stack and simulators like Apple is also the other widely used AV stack. Our hardware is a very typical autonomous driving car hardware configuration these days. Has a CPU, has the memory and GPU, and then because we need to run a simulator at the same time when we run the AV software stack, so we use 2 GPUs. One of the GPU just for running of the driving simulator at the same time, so we can simulate the driving scenarios of the driving analyzed with our framework. And the safety metric we consider in this case is as this, but basically it's derived again from the safe distance, just like our previous work I mentioned. And among the 4 categories of driving scenarios we just discussed, we give a little bit difference based on the driving parameters like distance, like speed of the car, and the acceleration of the car, and we measure using those formulas to measure the difficulty of the criticality of the safety criticality of the case, and among each of the category we pick either both the hard case, relatively hard case, relatively easy case, as noted in both letters in our study. So now comes our analysis results. Because due to the time, I'm not going to get into all of the numbers, but first is that we found that among all of the 4 scenario categories, the camera performance is the most safety sensitive parameter. That we change the camera FPS just a little bit, then we can impact the safety a lot. While the others are relatively will not lead to too much of safety hazard. If, say, we degrade the model precision or we degrade the GPU frequency, that will not impact the safety as much as a camera quality. And the noise that we introduce, our study shows that it depends on the longer or the shorter minimum distance. So case varies, and it depends on the detailed driving scenario. But in general, autonomous driving can tolerate as high as 50% of positive error. So that's quite over good fault tolerance for today's autonomous driving computer systems. When we fix because it actually, the camera FPS impact the safety a lot. So if we fix the FPS, well, introduce other entire model, what we found is that at low FPS, auto driving are less robust to errors, while at high FPS, vice versa. So these analysis with our frameworks, we just try to demonstrate what kind of thing auto driving computer engineers can do using our frameworks to help with their design towards the to guarantee the safety of their computer system. But the key takeaways from our analysis in particular is that we found that the default system can already tolerate the scenarios that are harder than the tested scenarios. And also there are quite a lot of opportunities exist for the system to optimize that to, for example, lower the GPU frequency that lead to more relaxed computation budget, but still maintain auto driving safety. And also others, the observation we can find. And the last, I'm going to quickly go over one of our ongoing work, some of the results we obtained over ongoing work, because it's still in submission. So I'm not going to get into too much of the detail of our design, but I can show some of the interesting results in terms of the system characterization that some of you might be interested in an autonomous driving system. So we recently did a system profiling on autonomous driving computer systems. So the computer system is just in general, like with CPU, with GPU, with memory, with storage, that I just discussed earlier. And at the same time, we use 2 machines with 2 separate GPUs to run the same, one run autonomous driving simulation and the other run autonomous driving software stack. And this study, we use the open source because the NVIDIA Drive Sim is not fully open source. So in this study, we rather, because we will publish all of our data as well. So we use the open source Apollo AV platform, AV stack. So what we found is that the first thing is that most of the previous safety study of off-road driving system is in general case, but there is a lot of corner cases that is safety critical that requires a very stringent reaction time. So as I put in here, like a cut-in or occluded cut-in. Occluded cut-in means that when you cut in, originally it's covered by some other obstacle that is invisible, that will lead to some of the sudden unexpected event that need a fast reaction time. Our profiling results show one thing. What we observe is that the performance or reaction time requirements and also the reaction time itself is highly dependent on or related to the traffic. So we actually, because in our previous works, when we collaborate with NVIDIA and also our field study, we found there's some relationship between traffic and the reaction time requirement and also reaction time itself. So this time, we want to quantize those. So we did a kind of analysis on the numbers and the curve that we draw. As you can see, there's a correlation that's very close. This shows the traffic, and this is show the latency, that is reaction time. So you can see a very similar shape of this correlation. The other thing is that we found the latency as varies across different modules. Like this is the planning, and this is prediction, and this is segmentation in the perception. So as you can see, average latency is very different, while the max latency is also different. And the relationship between the max latency and the average, like here, the maximum latency and the average latency, the difference is relatively small in the planning module, while here the bigger. So there's a lot of variation across different types of autonomous driving software tests. The other thing, based on our profiling, what we found is that there's a delay or there's accumulation of the reaction time or latency across different software tests. So for example, here, if say at the beginning, one vehicle rapidly coupling, that may lead to an safety critical event, then the camera capture it, the sensor capture it, but there's a delay of the perception module to start, and then there's a further delay of the prediction and planning module, and then there's long delay of the planning module because the calculation running behind the planning module is long. So until we can perform a true reaction to this event, this is already a long time. Right. So this is the reaction time it takes from the beginning of the this event captured by camera and until the actual reaction can be taken. And there's a lot of bubbles in there because of the delay that I introduced. So that's another thing that is less studied before in terms of system design. Now we need to consider. And another thing is that we want to show more detailed correlation between traffic and the latency. As you can see here, the number of points, that is the number of traffic, when it increases, the latency significant increase. And also, as you can see here, that also shows the number of like obstacles, like objects static or moving, like cars. When you have more obstacles around the car, then you can see the latency of planning and also prediction can increase a lot. But the way they increase, the pattern may be different across different software tests. And look at this distance, when it increased, the latency of reaction time also increased like quite a lot, right? And the last, we also profile the system level resource utilization, like the memory utilization. As you can see, there's a very close relationship or correlation between the last level cache miss inside the CPU if we run our algorithm on the CPU instead, and also the latency. And the CPU utilization pattern is kind of interesting because it's in a bursty manner. So for different modules in general, and most of the time, maybe kind of like a relatively flat in terms of utilization, but it may have burst and burst when there's some safety critical scenario comes up, so on and so forth. And we also have other types of characterization profiling results, as you can see, in terms of tail latency and so on. And we also found that this profiling results is that we profile the localization module software tests particularly. And what we found that for the that software test, the type of data that gets into the memory or into the data storage in general is highly related to the direction that the car is driving. So as you can hear, there's difference of the pattern or the data or the locality of the data, depending on in which direction the car is driving. Whether you're along the axis of your map, or you're turning actually with the angle of the map. So that will significantly impact the data format, access pattern, and also the locality. And also the memory utilization, it can change depending on where the car is driving and what kind of location, and also the driving, the manner and traffic, and so on and so forth. So that pretty much is everything I want to talk about. I think I used pretty much of the time. And we also across the other stacks, levels of the stack, if you're interested, you can take a look at our also recent work. For example, the Linux container to manage all of the self-driving car resources or functions, and when we deliver our framework first, we use just to use a robot, tour guide robot. But now this framework is already running on the autonomous driving vehicles on campus and UCSD. And we also recently study an efficient neural planner for autonomous driving cars. If you're interested, you can take a look at our paper to appear as well. And that concludes everything that I want to talk about today. And again, thank you everyone for spending time with me. And if you have any further questions, feel free to let me know if you have time, or otherwise, I'm also happy to talk offline. Thank you.
Thank you, Professor Zhao, for your presentation. So we open up this time for questions from the public. If you guys have any, please go ahead and ask the professor any question you have. No more questions? Okay. Well, probably.
Yeah, I guess it's a time. So if you're busy the next time slot, feel free to send me an email if you have any questions later on.
Yeah, please reach out to her if you want to continue conversations with her based on her work. Thank you everyone for coming. Thank you for presenting today. Awesome.
So Jishen, we have a couple of those one-on-one meetings scheduled with you. So you're just going to stay on the Zoom line here.
Okay.
Heiner is up first, and then he has, I think 2 students of his will be, I think we scheduled, is Peter or Suram in here by chance? No, I guess they're going to join virtually. But yeah, so Heiner should be on in just a moment.
Okay. Okay, sure, I'll stay here. Thank you.
Thank you very much. Oh, it looks like Suram and Peter are in the Zoom. Suram and Peter, were you guys going to join with Heiner or after Heiner? Because I saw he signed up for the first slot. Sorry?
We're joining after.
Okay, great. Thank you. Okay, so you guys can go ahead and hop out. Jishen, I'm going to make you the host.
Okay.
So the schedule, he should be here in just a moment, hopefully. Looks like 3:05 to 3:20 will be Heiner, and then Suram and Peter will hop back in at about 3:20, and they'll be in together, and you'll be wrapped up by about 3:35.
Okay, is there any chance that Suman and Peter, we can move, like shift 5 minutes early, because I might need to leave by 3:30.
Yeah, I'll send an email in that email thread that I sent before to all of you
Or
guys.
if no, I can also post. I can also stay for 2:30.
I mean, that should
That's
be
also fine to me.
Yeah, if you need to run, let's not keep you longer than we need to. So I'll send them an email and just say, hey, let's wrap up by 3:30.
Okay. Sure.
Okay. All right. So I'm about to make you host, and then
Thank you.
on out. Let's see. Okay, great. Thank you, Jishen.
Thank you, Eric. Have a good rest of the day.
You too.